Hello everyone, today I'll talk about the solution to the problem minimum number of days to disconnect island. Feel free to pause the video and read the statement. In this problem the bounds are small enough that we can have a solution that's quadratic with respect to the number of cells in our grid easily. So it doesn't have to be just height times width, it can be, for instance, height times width all squared. So how do we approach a problem like this? Now typically when you have something that wants a minimum number of days to disconnect island, a nice idea is to first think about what would happen if we were looking backwards in time and trying to connect island, because we can easily connect things using DSU and not easily disconnect things. However, in this case, this is not a fruitful approach because we choose the elements that we want to remove. So we want to remove land cells, we want to remove the fewest land cells to disconnect the whole island. So the essence of the problem is which land cells to remove optimally. Now, at first we can notice that there is no requirement when it comes to the shapes of the islands that remain after we remove our land tiles. In particular, those can be two big islands, and we can imagine a case where two big islands are a result. So for instance, we could have a big island here, a big island here, and a small bridge connecting them. So in that case, we will split off into two big islands. But there is never a case where we really need to remove that many land tiles to split off some part of the island from another. Because of course, in that case, one would be enough. But if, for instance, there were three different bridges, then we would have to remove three elements to split off those two big islands. But for instance, if we have an element like this in the lower left corner, or in any corner really, then if we only remove what's above it and what's to the right of it, then we immediately have disconnected the islands, because now this element is an island in itself, and the rest is an island in itself. And it's easy to see that we always can find an element like this. Because of course, you might wonder what if there is no corner, but for instance, sometimes if an element is just sticking down, then we only need to remove this element. And it's easy to see that there can be no island where every element is neighboring at least three different elements, because at the end, even if you try to extend the pattern like this, you will reach a wall. And after you reach one wall, you will reach another wall or a water cell. And in that case, this would be one land cell that has at most two neighboring land cells. So the number of steps is not that big, and in particular, if we cannot do it in 0 steps, because we have, for instance, no islands at the beginning, or already more than one island at the beginning, and if we cannot do it in one single step, then we know that we can do it in 2 steps and we return 2. So now the problem has transformed into being given an island, trying to find if flipping a single land cell will make that island disconnect. And you can bring out the big guns at this point. You can bring out some algorithms for finding bridges and articulation points in graphs, because now simply we just want to find if there is an articulation point in the graph represented by our grid, which consists of low function and so on. It's not a difficult algorithm, but of course it's an algorithm, and it's likely that if this is a problem that you're given, for instance, in an interview, that the interviewer might not be very familiar with that algorithm. So that is one approach, and it's good to know that this approach can be utilized. However, as I mentioned, the bounds in this problem are not too big. So we can also use a more brute force approach of just trying every single land tile, modifying the grid accordingly, and seeing how many islands are on that grid. And this is the solution that I'll show you. We need the standard boilerplate, height, width, directions of neighboring. And now, the essence of the algorithm will of course be a recursive function for marking the whole island as visited. So we start at some point, we mark it as visited, and we visit, in this case, again, like in yesterday's problem, it is a DFS. So we just recursively, or in this case we simulate the recursion using a stack. We look at all the neighbors, if they are within bounds but not visited, we mark them as visited and we visit them. And if we go through all the possible elements on the grid, so for instance we want to get the number of islands in the original grid, we go through all the possible starting points, and if it's still a land tile, that means that it was a land tile at the beginning and we never removed it as part of another island, then we know that this is another island, and we try to sync that whole island. And of course we want to, as appropriate, make deep copies of our grid so that we still have the original grid whenever we need it. So at the beginning, if island count is not equal to 1, so either it's 2 or more, or if it's 0, then we don't have to do anything for the island to be disconnected. Now, this is the essence of the quadratic algorithm. We will go through all the possible land tiles. We create a copy of the grid with that land tile removed, and we count the number of islands remaining on that grid, which is exactly the same as before. And again, if that island count now is not equal to 1, then we don't have to do anything else. So we have done one removal and we return 1. And at the end we just have to return 2, because we never, as we mentioned before, never have to remove more than 2 land tiles to disconnect the island.